Hello there. It's raining. I really hope you can make out what I'm saying. So, today let's solve this question from the Berkeley Math Tournament of 2021. This is the last question in the calculus test. The most important, stuff that you need to do in order to solve this question is finding the Taylor series of a few functions and to convert the multiplication here into addition, into series using the natural log. So the first thing that we should do is to find the partial product. So we denote this by p sub n. So that would be pi over 2 to the power of capital N. And the rest is just pi, capital Pi, n equals to 1 up until n of a tan. I'm just going to use a tan because it's shorter. A tan n over a tan 2n a tan 2n minus 1. Hi, this is me from the future. I just realized that I didn't cover the full proof. So the way we're gonna go about doing this the proper way is to prove using induction. So first off, we'll start with our base case. So we're just gonna go ahead and evaluate the first few n. Let's look at n equals to 1. That's just a tan 1 over a tan 2 a tan 1. So this cancels out to yield 1 over a tan 2. Okay, so let's look at the case for n equals to 2. Again, we carry this into n equals to 2, so that's a tan 2, and obviously this is going to be canceled out. A tan 2, this is divided by a tan 4 and a tan 3 in the denominator, and obviously this also cancels out to yield 1 over a tan 3 a tan 4. So you might see where this is going, but we're going to do a couple more examples just to really see it. So n equals to 3. We'll carry this whole thing over. So that'll be a tan 3 a tan 4. And obviously when we get into a tan 3, that's going to get canceled out again. So that's a tan 6 a tan 5. Okay, that cancels out. Again, we see the same pattern happening over and over again. A tan 4, a tan 5, and a tan 6. Okay, and obviously for n equals to 4, it's going to repeat over and over again. We can pick any for our base case. We're just going to pick 3. So let's say we have a natural number k equals to 3, where this holds true. Let's call this expression S3. That'd be 1 over a tan 4, a tan, just multiply it all the way up to a tan 6. Okay. Now let's look at the number after 3. So now we add 1, k plus 1, 4. So S4 is going to be equal to S3 before it. Multiply it by a tan 4 over a tan 8 and a tan 7. Now we see that we basically have 8. If you notice this, what we have in here is S3 multiplied by a tan k plus 1 over, a tan 2 k plus 1 a tan 2 in bracket k plus 1 minus 1. A tan k plus 1, which is what we see in here, a tan k plus 1 multiplied all the way up to a tan k 2k. This is going to get canceled out. A tan k plus 1, a tan 2k plus 1, a tan 2k plus 1 minus 1. This gets canceled out. And what we're left with is k plus 2, 3, and so on until 2k. So now what do we observe? Let's just reorder the terms under. So that would be a tan k plus 2 all the way up to a tan 2k. Again, same thing. A tan 2k plus 1 in bracket minus 1 multiply all the way up to a10 2 multiplied by k plus 1 in bracket. So what do we see here? So this is basically equal to 2k plus 2 minus 1. This is just equal to 2k plus. That means that this is a direct succession from this. This is a10 2k. And this is exactly what we want to prove, which is that for Sn, it will always be equal to a10 n plus 1 all the way up to a10 of 2n, obviously to the power of negative 1. It's just more compact way. So we can make it even more compact by writing it like this. So pi is n equals to n plus 1 up until 2n of arctangent n 1 over. Since this is to the power of negative 1, this whole thing to the power of negative 1, we could just bring it down in front of the natural log to become minus. So that'll be a10 n with n equals to n plus 1 up until 2n. So the good thing about Taylor series is that it's easier to analyze. a10 of 1 over x is equal to the limit as x tends to 0 from the right hand side, a10 1 over x, that'll be minus 1 over a squared plus 1 x minus a plus the remainder terms, so that'll be x cubed. There's no x squared there because the x squared term gets multiplied by 0 due to the derivative. Okay, so this would be the Maclaurin series because a would be equal to 0. And this thing right here, it evaluates to pi over 2. So pi over 2, this is just 1 with the minus sign and x. So that'll be minus x plus this remainder term. Let's take the substitution, n equals to 1 over x. Now, as x tends to 0, n tends to be a very large number. If we take the limit of x from the right-hand side, what we get is a very huge positive number, which is exactly what we want. Take the substitution and we get a10 of n equals to pi over 2 minus 1 over n plus the remainder term. So that'll be n cubed. But you might ask, why don't we just take the Taylor series directly, compute the Taylor series or Maclaurin series for a10 of n? Oh yeah, I forgot. This thing has not yet become a series. So you might notice that this is a bunch of repeated multiplication inside of the natural logarithm. So since we have this negative sign in front, that means when we decompose this thing, it's all gonna be minus the sum from n equals to n plus 1 up until 2n of the natural log of a10 of n. We'll plug this new expression, this Maclaurin expansion for arctan into here. So this would be, I guess we'll just put it into this blue expression here. So this would be 2n n plus 1 of natural log of pi over 2 minus 1 over n plus O 1 over n cubed. Okay. How do we reduce this into something we can work with? Well, the answer is, again, Taylor series. So we're going to take a look at the Taylor series for ln of x. Centered at a equals to 1. So that would be ln of x plus 1 equal to ln of 1 plus 1 over a multiplied by x minus a plus the rest of the term. So that would be x squared. So this is just x plus 0 x squared. Take a look at this expression right here. I'm just going to copy this again. And we can factorize p over 2 out. So that'll be p over 2, 1 minus 2 over pi n plus o of 1 over n cubed. So we're going to get natural log of pi over 2 plus natural log of 1 minus 2 over pi n plus o over n cubed. This is where the Taylor series of ln of x set at a equals to 1 is useful. X equal to negative 2 over pi n. So this is ln of pi over 2. We finally managed to express this part of the sum with a nice algebraic expression. So we're just going to substitute it back in. So this would be ln of pi over 2 minus 2 over pi n. Now we could just split this summation, ln pi over 2 minus of ln pi over 2 plus the sum right here. I'm just going to take the 2 over pi out. So this would be n, just n. And so this can be further reduced into minus. Okay, so that would be 2n minus n plus 1 minus 1 multiplied by ln pi over 2 plus this thing. There it is. Okay. So this just reduces to n, so that cancels out entirely. So we get 2 over pi up until 2n and equals to n plus 1 over n. Now this is the last, I guess, trick that we're going to use, which is the Riemann sum definition of a definite integral. We can multiply by 1, n over n. Alright, so that'll be 2n minus n plus 1 minus 1 over n. And this just fits exactly with what a typical Riemann sum looks like. And we're only multiplying it by 1. So if we take the limiting case as n tends to infinity, so 2 over pi, limit as n equals goes to infinity, of this whole thing, what we actually get is a definite integral going from n up until 2n of 1 over x dx. So all we have to do now is to integrate whatever is in here. So that would be 2 over pi ln of x going from n up until 2n. So that would be 2n over n, and this is finally equal to 2 over ln of 2 over pi. So that completes our answer.